尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, welcome everyone to the Wednesday session of the meeting. That's been great so far. And today we have only the morning session, and it promises to be wonderful. And we start off with Nati, who will tell us about proliferation transitions from a 2+1D TQFT.
Thank you. I hope you can hear me. I hope you can hear me. I'd like to join everybody else here, thanking the organizers and the sponsors for putting together this very interesting conference in this spectacularly beautiful place. If you haven't done so, I recommend that you walk around. And you should do it both during the day and during the night because it looks completely different. This will be a quantum field theory talk based on joint work with Monk Cheng. It's a paper we wrote in March, and there is a paper extending it considerably, which is in preparation, and I hope that the zero here is not too optimistic. So it's common to have maps between field theories in general, or in between 2+1 dimensional field theories, and for the purpose of this talk, we'll talk about maps between 2+1 dimensional topological field theories. But I emphasize that whatever will be on this slide will be a map between two theories. There is no dynamics. There's theory number one, and we map it to theory number two. And how do we do it? Well, the simplest thing we can do is take what we have in tensor decoupled sector. The condensed matter people refer to it as stacking. We just stack another theory. This is kind of obvious. We can also couple the system to ordinary gauge fields, and there are several different ways of doing it. Some of them will appear later in the talk. we have a field theory and we couple it to gauge fields. A slightly more sophisticated thing is that we have an anomaly-free one-form global symmetry, and we can gauge it. So we map the original theory to a theory where we gauge the one-form symmetry. And for some reason, I'm actually partly responsible for that. It's being referred to in the literature as anion condensation. And I feel extremely strongly that this term is misleading, and it's unfortunate that it's called that way. And hopefully by the end of the talk, you will see why this commonly used term is actually misleading. And then you can repeat this process again and again. So here, as I said, we'll focus on 2 + 1 dimensional quantum field theory. And just to have an example, so imagine you're trying to do, this doesn't work. So an example of, okay, my pointer just died. Okay, so if you look at the first thing, the tensor product, imagine you have SU2 level K, and you can tensor U1 level K prime. That's not too difficult. Gauging a zero-form symmetry, an example would be take a U1 Chern-Simons theory and turn it into an O2 Chern-Simons theory. The third thing is taking a quotient of the gauge group. So for example, you have SU2 Chern-Simons theory, and you turn it into an SO3 Chern-Simons theory. And we can repeat this process again and again. So as I said, we should really distinguish between the different operations, and especially the one that is gauging a one-form symmetry is really taking a quotient of the gauge group. So we have one field, one TQFT, and we map it to another. Question: can we find a non-topological field theory where we have a phase transition between theory number 1 and theory number 2? Can we have a parameter in a non-topological theory which, as we dilate, on one side, sign of the parameter, we have the original TQFT, and for the other sign, we have the other one? For example, can we achieve any one of these steps by such a transition? This is a dynamical question. It goes outside the framework of TQFT. And what I'll present in this talk is examples of how this can be done in a quite canonical and natural way. And as a way of application, imagine you have a system in condensed matter physics, and it has phase 1 and phase 2, and we dial some parameters, so we have a phase transition from phase 1 and phase 2. What can we say about the phase transition? If it's second order, we can predict the critical exponents and so forth. This thing really doesn't work. This is the problem with technology. Okay, so we have in mind some non-topological theory, which I'll call the UV theory, which has 2 phases, T and T prime. And we dial a parameter, for example, the sign of the coefficient of a phi square for a scalar field. And as we dial the parameter, the system undergoes a phase transition. So far from the phase transition, we could be in one phase or in the other, and our goal is to go outside this framework and describe the transition. So what do we see as we approach the transition? If we are on one side, there are some heavy anyons, but from the point of view of the TQFT, these are merely defects in the TQFT. They have no dynamics. But as we dial the parameters and approach the phase transition, one or several anyons become lighter, and we should think of them as being dynamical rather than just defects. And then they can trigger the transition. So what we're going to do is look for such a field theory which describes the transition, and we'll refer to it as a transition field theory, or the transition theory, which goes outside the TQFT. And for simplicity, I'm going to limit myself to the anyon becoming light. This blue italics character Q will be an abelian anyon. That means that as I take any defect or any anyon and I fuse this one, what I get on the other side is a simple anyon, not a linear combination of them. So this is a very natural assumption, and you will see that with this assumption I cover most of the literature. So it's not a drastic assumption. And I emphasize that T could be arbitrarily complicated. It could be extremely complicated, the TQFT. Being abelian, this anyon generates a Zn one-form symmetry. The way to find the n, or the order of the anyon, is we raise it to the nth power, we find a trivial anyon. So we have a finite number of anyons altogether. This is an abelian enyon, so we have q, q squared, etc. Q to the n is 1. And as a symmetry, it has an 't Hooft anomaly. And the 't Hooft anomaly is determined by the spin of the enyon q, which on general ground it's p over 2n mod 1. And I emphasize that in the context of TQFT, only h mod 1 is meaningful. In field theory, h itself is meaningful. This is the spin of the particle. But in the TQFT, only h mod 1 is meaningful. So our goal is to find such a theory. The input is a theory T, TQFT, and a dynamical Q. And we could look for a Chern-Simons theory. This would be the obvious guess. We write a Chern-Simons description of T, and Q would be an enyon there. So that should be easy. We just take a scalar field in an appropriate representation of the gauge group, and then study Chern-Simons theory, Chern-Simons matter theory, and we heard a beautiful talk about that yesterday. So the first obstacle we have, or the first difficulty, is that this procedure is not unique. For the same TQFT can be given an infinite number of different presentations of Chern-Simons theories, different gauge groups, different levels, and we should ask ourselves, do they all lead at the level of TQFT, they are all the same, but are they going to lead to the same field theory and therefore the same transition? Even if we choose G, this gauge group, even if we choose it, for the enyon Q can be represented typically by an infinite number of different representations of the gauge group. For example, U1 level K has K different enyons, and the group U1 has an infinite number of representations. Will there be a difference if I choose different representations or not? So it's one of these things that at first sight it looks, how can we possibly do it? And at second sight we look, well, there's so many ways of doing it, so how should we proceed? And finally, the enyon Q might not even be associated with the representation of the gauge group because it could be magnetic. So what do we do then? So I'm going to make one simplifying assumption, that the scalar field that I throw in phi is a single complex scalar field. That's the assumption I will make and see how far I can go with it. So now we'll have a little detour, and we'll have a little exercise in TQFT. So given a TQFT and this enyon that we chose, we're going to map it to another TQFT, which I'll denote as T prime. And this would look like a construction that I pull out of a hat. Actually, from the math perspective, it's very natural, but also from the physics perspective, it's very natural. But let me just proceed just presenting it. So we started with T, which has a Zn one-form symmetry. I'm tensoring U1 level minus NP. So remember, option 1 in maps between theories are just tensor a decoupled sector. So T had Zn one-form symmetry with anomaly P. This has Zn one-form symmetry with anomaly minus P. So I picked a particular thing to put here on the right-hand side, which has the opposite anomaly, so that I can gauge the one-form symmetry. The symmetry that I gauge, I denote it here. It's the enyon Q from here, in the U1 charge P enyon from here. So this is well-defined gauging, and we find another theory. And noting that T prime depends on the starting point T, the enyon I chose Q, and therefore its order and its anomaly. But the result we get depends also on P as an integer, not only on P mod 2n. And although it's not obvious from here, this operation can be phrased as related to Witten's SL2Z operation, which was also a map between field theory. You start from field theory number 1, you do a certain transformation, and you produce field theory number 2. So this map here from T to T prime can be phrased in a similar way. Now let's make it a little bit more complicated, and instead of putting this U1 level minus NP in the numerator, we'll put a slightly more complicated theory. So this factor is the same as that one, and now we add another gauge field C, and we add another term here. So we place this thing in the numerator. More mathematically, if you're so inclined, this T and P is a TQFT, and it's the Drinfeld center of the original Zn one-form symmetry we're talking about, but let's ignore this technicality. So if we repeat this procedure above, we tensor this and mod out by Zn, roughly speaking, the C that we added kills B, and we end up where we started. So this thing was invented by my student Po Shen Shin, And we used to call it Pochent's trick at the time because we didn't fully understand it, but it always worked. So this seems like a very complicated mouthful way of saying the following. We started with T, and here is a more complicated way to present the same T. What did we do? We added something and we gauged the one-form symmetry, and in the end we have the same thing we started. However, the advantage of doing it is that the anion, which is the hero of our story, Q, is represented as a simple Wilson line of C in this construction. So we took the complicated TQFTT, and we managed to peel off in a billion anion out of it. And the TQFT is complicated, the construction is complicated, but this abelian anion is represented as a simple Wilson line with charge 1 under a U1 gauge field. This allows us to construct the transition field theory. So we start with the same TQFT, we present it in this form, which is admittedly more complicated, and we add a scalar field phi that couples to C with charge 1, and now we have a mass term, and we can add quartic couplings and higher derivative terms, etc. So this is the theory. Given the TQFT we started with in Q, we added phi in such a way that the operator phi creates the anion that we are interested in, the hero of our story. The spin of this anion is P over 2n, except that here the theory is non-topological, and therefore the spin, and not only the spin mod 1, is physical. So what we have now, the data is T, the choice of anion Q as another integer. And at this point, earlier I said we should not study P equals 0 because it's the U1 level minus NP for P equals 0. It's strange, but in this case we can consider this theory even also for P equals 0. So from this point on, for the coming slides, I will just analyze this Lagrangian. This looks like a completely straightforward exercise in field theory, in Chern-Simons matter theory. This is the Lagrangian. I spelled out everything. Let's see what the symmetries are, what the phases are. We just follow our nose. So first, we had some one-form symmetry of the original TQFT. Since we have matter fields, that one-form symmetry is explicitly broken to a subgroup. That will soon have another interpretation. More interestingly, the TQFT does not have any zero-form U1 symmetries. This Lagrangian has a zero-form symmetry because I can take phi and multiply by an arbitrary phase. So we have a U1 symmetry. There will be a question of how to normalize the charge, and we'll do that in a lot of detail. But we note that we lost some one-form symmetry, and we gained a zero-form symmetry. What are the phases of this theory? Let's start with P not equal to 0. When mu square is positive, the mass square of the phi that we added is positive. So it's just a heavy field. We can forget about it, and we have our starting point, the TQFT. When mu square is negative, the scalar field phi hixes the gauge field C, and we end up with a gapped phase with this TQFT. So what we see is that our transition field theory induces a transition from the original T to the other T. Interestingly, this map from T to T prime in this particular case coincides with something that the condensed matter physicists have already studied. This is known as the hierarchy construction of Haldane and Halprin. What they had was a fractional quantum Hall system with some anyons, and then you take more of these anyons, and these anyons interact, and they form their own quantum Hall. So intuitively, I understand that, but I feel a lot more comfortable when I see a field theory that does the job, and here it is. So now we see that this description of the original state and the hierarchy construction coming out of it is really a Higgs transition in this Lagrangian, which gives us a very detailed picture of what the transition is. For P equals 0, for positive mu square, we still have the original TQFT, not any different. But when mu square is negative, the theory is gapless. This is obvious if we just look at this formula. The level of the U1 is 0, and therefore we do not have this theory. What is going on here? So we do not have this U1 factor, so the model is gapless. And indeed, I said that the model has a global U1 symmetry. The model has a global U1 symmetry with an operator O carries charge 1 under it. And in this phase, O has an expectation value as breaking the U1 symmetry, and the model is gapless. So what should we do about it? Since we have spontaneous breaking when the operator O gets an expectation value, let's add it to the Lagrangian. When we add it to the Lagrangian, we explicitly break the U1 symmetry. The gapless phase becomes gapped. And now we have a map from the original TQFT T to a Z-n quotient of it, which is gauging the one-form symmetry. So what this field theory does is it implements a transition of gauging a one-form symmetry. I emphasize that conceptually, gauging a one-form symmetry is completely different than Higgs transition. We added more gauge field, and the other one, we Higgs something. One is a map between field theories, and the other is a dynamical process. And now we see that this transition implements the gauging. And from this perspective, the breaking of the one-form symmetry of T that I mentioned in the transition theory, if we think of it as gauging, that's the ABJ anomaly in the TQFT. So the TQFT person who has this transition would say what we have is ABJ anomaly, which kills a one-form symmetry. And the person who looks at this transition theory would say, no, this is a classical phenomenon that the coupling to phi explicitly breaks the symmetry. And surprisingly, the zero-form symmetry that I discussed is also interesting. When we gauge a one-form symmetry, we typically get a dual or a quantum zero-form symmetry. This is familiar already from orbifolds in 1+1 dimensions. When we perform an orbifold, we get a quantum or dual zero-form symmetry. Here, that symmetry acts on lines in the TQFT. It can permute lines, it can act on vertices, and so forth. And now we see that our more complicated transition theory has that zero-form symmetry as an exact symmetry across the transition at every phase, including in the UV, which I found right surprising, and you will soon see that it's kind of subtle. Now, I should also mention the closely related construction was not published, but was found by other people. So this was all very abstract. Let's take a concrete example and see it at work. So let's start with SU2 level K. This is a non-abelian theory. It has a one-form symmetry, Z2 one-form symmetry. So the relevant anion, which is the hero of our story, is the spin K/2 representation of SU2, and it has some level of P. If P is not zero, our transition theory produces a map from SU2 level K to this slightly more complicated TQFT. And if we substitute P equals K, the theory on the right-hand side after the transition is the parafermion theory. So what we have achieved is going from SU2 level K to the parafermion theory as a Higgs transition. That you asked me several years ago, is the relation between SU2 level K and parafermion, these look like two totally different constructions. Here we see that this is a natural special case of this transition theory. And if P is zero, we said that the transition is to a gapless phase. There's a natural monopole operator that carries charge under the U1, which is spontaneously broken. And if we add it to the Lagrangian, we see a transition from SU2 level K to SO3 level K. This is the surprise that this gauging, or taking a quotient of the gauge group, which is completely different than Higgsing, this is implemented as a Higgs transition. So this gave the general construction, and I gave this example to show you how it works. And now, what I'm going to do now is discuss the zero-form symmetry in a little bit more detail, because there's an interesting subtlety here in field theory that I at least had not seen before. Maybe some of you have seen that before. So without phi, our TQFT T, there was no zero-form symmetry. So the TQFT does not have U1 zero-form symmetry. All the magnetic charges are zero because of the equations of motion. With phi, there is a global U1 symmetry, which we can take to multiply phi by a phase. We have a scalar field, we can multiply it by a phase. Example to keep in mind, in QCD, we start with a SU3 gauge theory. There is no zero-form symmetry. We put the quark in. There is a zero-form symmetry, which is baryon number. It will be very interesting to see what the proper normalization is, but the current is just phi bar d phi. If we look at the equation of motion of C, we can see that this current can also be written as the magnetic symmetry for B. So at the level of the TQFT, the left-hand side is zero by the equation of motion, but once we add the scalar field phi, there is a current, so it can also be viewed as a magnetic symmetry. So up to coefficient, The current we are interested in is this one, and our goal is to find the coefficient. So intuitively, phi creates the anion Q. It's not gauge invariant, so it must be attached to a line, which is a Wilson line. The presentation of the Wilson line is particularly simple in our Lagrangian because this is just a Wilson line for C. The anion Q to the n is a trivial anion in the TQFT, so phi to the n creates the trivial anion, and therefore this should be a local operator. And indeed, it can be dressed by monopole operators in the theory. At the level of Chern-Simons theory, this is clear. The trivial anion is also a Wilson line, but it can end on a monopole operator. In the analogy of QCD, phi is like the quark, and this is like the baryon operator that carries charge 1 under the U1 symmetry. However, here, so one would say, okay, O has charge 1, and this sets the normalization of the current. But it's not so simple, because in the TQFT that we discussed, we had to gauge this one-form symmetry. And that means that the gauge field B can have fractional fluxes. And if it can have fractional fluxes, we can raise the monopole operator to a fractional power. So we might be tempted to study another operator, which is also gauge invariant, phi raised to a fractional power, and some monopole operators to dress it. These are valid monopole operators in the TQFT, so we could ask, what is the integer L? This is what's the normalization of the coupling, and what's the significance of O prime? In the analogy with QCD, if the quark has charge baryon number 1/3, and the baryon number of all the gauge invariant operators have integer baryon number, this would be a gauge invariant operator that carries fractional baryon number. Is there such an operator or not? And how should we determine it? I claim that the answer is yes. So this is the summary of what we are. We have a current with the normalization to be determined. We have O, which is clearly a well-defined local operator. And there's an O prime, which is a candidate to be a local operator, but it's more subtle. So phi creates the anion Q. We have already said that. O creates the trivial anion Q to the n, and hence it's clearly a local operator. O prime creates a non-trivial anion because it has phi to a fractional power, not fractional, phi to the n over L. This is an integer, but not n, smaller than n. So it creates a non-trivial anion, and therefore it must be attached to a line. So here it is, and it is attached to this blue line. But this blue line can end, not on a regular monopole operator on the sphere, but it can end on a monopole operator on a high genus surface, either genus 1 or genus 2 or others. In other words, the fluxes, the fractional fluxes that we need in order to construct this object exist only on high genus surfaces that do not exist on the sphere. So this thing is possible if and only if in the T that we started with, before we added phi, for some genus there is a state with this anion sticking out. And it's easy to construct examples where this is the case. And this is possible if and only if this anion, although being non-trivial, it is invariant under all the one-form symmetries in the problem. This takes a little bit of work to show the if and only if, but that's the answer. So what's going on here? The local operators that act at a point, like O, realize faithfully only a quotient of the global symmetry group. So we have a U1 zero-form symmetry, and the local operators, like baryon operator, realize only a quotient of the gauge group, of the global symmetry group. And closed line operators, like O prime, realize faithfully the whole global symmetry. So in order to find the proper normalization of the charge, we need to understand how operators act not only as points, but also how they act on lines or high genus surfaces. Now we can deform the theory by O, but we cannot deform it by O prime. And that's exactly what we did before. And as we do that, the symmetry is broken, but it's broken to a discrete symmetry. And surprisingly, this symmetry typically acts on T prime, where it indeed acts on lines. And as such, that is the example of the dual symmetry that we saw when we gauged the symmetry. So what we see here is a non-trivial mixture between symmetries that act on point operators and symmetries that act on line. In hindsight, it does not contradict everything. It does not contradict anything, But I, for one, was extremely confused by that, and I'm happy the way it works. And what it tells us that this transition field theory is smart enough to have all the correct symmetries that we need on the two sides. So Rajesh is trying to kick me out of here. Whoops, this doesn't work. So let me summarize. Anyon condensation is a misleading name for gauging a one-form symmetry. Gauging a one-form symmetry is a map between field theories. Condensation means that there's a dynamical process. In this particular dynamical process, also nothing condenses. If at all, there is a Higgs transition, and the Higgs transition is no condensation. And better word here is proliferation, but what proliferates is not the anyons, but the anyon lines. So an example to keep in mind is the BKT transition should really be thought of as a proliferation rather than the condensation transition. And here, it's the lines that proliferate. Gauging a one-form symmetry is the same as proliferation of anyon lines, and it's achieved here by a phase transition described by a well-defined local field theory with Chern-Simons term and a Higgs mechanism, and it depends on T and the anyon we're talking about and another integer P. So all the complications we said before, there are infinite ways of doing it and many different gauge groups and all that. All this freedom boils down to one integer in the end of the day. Everything else doesn't matter for the transition. And we presented two classes of examples. If P, this anomaly, is 0 and the integer is 0, we found a phase transition that performs the gauging of the one-form symmetry. The one-form symmetry is presented as Higgsing a gauge field. And for P not equal to 0, it's also interesting, and it leads to this hierarchy construction of Halprin and Haldane. Now, I've not done it here. I have spare slides that I don't think Rajesh will let me show, where we can easily generalize it to several billion anyons. A billion anyons that might be non-local relative to each other and to themselves. In fact, you can peel off the entire abelian sector of the TQFT and leave something else complicated, and every manipulation of the abelian anyons can be done using relatively simple field theory techniques. What we have not done is to extend that to higher representations, and even more interestingly, to consider non-abelian anyons that correspond to non-invertible symmetries. What happens when they proliferate? I think this would be actually extremely interesting to work out, but we haven't done so. And I apologize for going over time, so thank you.
Okay, hopefully no proliferation of questions, but we can have a few. Sorry.
Hi, thank you. I was wondering, for this operator O prime, you discussed the idea that the operator O prime gets a non-trivial defect Hilbert space on some higher genus surface, if and only if it's invariant under part of the symmetry. Can you explain how you prove that in this case? This is a general conjecture about breaking of non-trivial
It's not a
symmetry.
conjecture. This can be proven in one. It's if and only if in one direction it's obvious. If it's not invariant under the one-form symmetry, I can surround it by the generator of the one-form symmetry and remove it, and therefore it has to be 0. In the other direction, it's easy to, it's not so obvious, but there's a way to prove it, which will be in our paper. We basically check the dimensionality of the Hilbert space with a defect using the Verlinde formula, and you can get a certain inequality and show that it's not 0. But the second step takes more work. And I got to say that we got help from ChatGPT on this.
Yeah.
Hey, Nadi. Can you re-explain the distinction between the anyon line and anyons?
Yeah, so the anyon, in the TQFT, I guess that's what you asked, there is no anyon. There is a defect, which is a line, and therefore people talk interchangeably about the anyon and the defect. The condensed matter people think of the anyon as a particle, hence the on at the end, like proton, electron. So this is a particle, and the defect is the word line of that particle. So when you say that normally that particles or a local operator gets an expectation value, for example, when a symmetry is spontaneously broken, it's not the line gets an expectation value, but the local operator gets an expectation value. Now, condensed matter people call many different things condensation, including the name of their field. And what that means is that you have the origin of the name is you have a lot of something. So when you have vapor in the air and it condenses on your windshield, that's also condensation. Then when you have a symmetry which is spontaneously broken, then what you have is you have an operator that gets an expectation value that spontaneously breaks the symmetry. This is different than what happens on your windshield. This is also referred to as condensation. Then the BKT transition, no symmetry is spontaneously broken, but instead what you have is explicit symmetry breaking. This is because you deform the Hamiltonian by a relevant operator that explicitly breaks the symmetry. Some condensed matter physicists refer to that also as condensation. Others complain, no, they don't know what they're talking about. In the anion condensation, we just adds that to the mix. It's another fundamentally different phenomenon with the same word. Personally, I find that very confusing to use the same word for different things. So I'd like to avoid, for the windshield, I'm happy, but for everything else, I think this, or maybe for spontaneous symmetry breaking, like a superfluid. But other than that, I think this word should be avoided because personally, I find it very confusing. Especially here, that we had three or four different things that happening, and calling all of them the same is enormously confusing. I'll be happy to explain that in more detail.
Okay, in view of the time, we'll postpone further questions for the tea break. Thank you, Nati. So the next speaker is Shinan Zhao from KITS, and he'll tell us about giant gravitons as defects.
Thanks, Rajesh. And first, I want to thank the organizers for the opportunity to speak at Strings. So today, I'm going to talk about giant gravitons from the perspective of defects. So this talk is based on collaboration with my student Junting Chen and Winfeng Jiang, who's a faculty member at Southeast University in Nanjing. So let me start from the familiar success story. So in n equals 4 supreme mills, we know that we have a remarkable amount of control in the planar limit. So at a weak coupling, we have the planar Feynman diagrams. At a strong coupling, the theory is described as classical supergravity in ADS. And in particular, correlation functions can be efficiently bootstrapped as amplitudes in ADS. Moreover, at finite coupling, we have also integrability, which gives another useful handle. So the planar regime is well under control, thanks to many exact tools. Perturbatively away from the planar limit, there has also been a lot of progress, allowing one-over n corrections to be computed. For example, at strong coupling, we can use the ADS version of the unitarity method. Also at weak coupling, there are integrability-based constructions. But we should also realize that most systematic progress is restricted to light probes, which do not scale with n. For example, we often look at these BPS operators, which are built from a product of states, a product of fields as a single trace in color space. Moreover, even though we can compute these one-over n corrections to low orders, this is still quite far away from the truly finite n physics. Of course, finite n is a very difficult problem, so what I want to keep in mind is if we can, but they are still controlled enough so that we can make progress. So the giant gravitons are a good target in this sense. So in the field theory description, the maximal giant, which is what I will focus on in this talk, is represented as a determinant operator. So these giant gravitons, they are also have BPS operators with protected conformal dimension delta equals to n. So they are not light excitations like the single trace operators. And also the determinant color structure changes to 1 over n orders, as is clearly visible in these different 3-point functions. So the giant gravitons are a good target that sits in between. They are BPS enough to control yet heavy enough to retain genuinely non-planar physics. So what has been known about these giant gravitons, more precisely about their correlation functions? So traditionally, these objects are viewed as correlators of light and heavy local operators. So the simplest example is the three-point function, where you have two determinants and one single trace light operator. But three-point function is fixed by symmetry up to a constant, and if the light operator is also protected, then this constant is even independent of coupling. The next simplest case, which has a non-trivial space-time dependence, is the four-point function, where you have two light operators. At weak coupling, more progress has been made, so these correlators have been computed to a few loops. At strong coupling, on the other hand, there's been essentially zero result, except for a localization prediction for certain integrated correlator, when both light operators are in the stress tensor multiplet. Of course, there's nothing wrong with this local operator perspective. It's just this may not be the most useful one. And it turns out that the more natural way to view these giant gravitons is to view them as some special kind of zero-dimensional defect. So why is this defect perspective more natural? So this is the most clear from horography. So via ADS-CFT, the determined operator is due to a D3 brane, wrapping S3 instead of S5. So in the ADS directions, we have a one-dimensional word line that can be naturally identified as some line defect. Now, generally in ADS-CFT, objects in ADS become one dimension lower when you move that back to the boundary. So these one-dimensional word lines in ADS become defects on the boundary with 0 dimensions. There is also a symmetry way to say the same thing by analytically continuing the defect dimension. So when we have a p-dimensional conformal defect, the d-dimensional conformal group gets broken into that of p dimensions times the transverse rotation. Now this continues to make sense, even when we extend the value of the defect dimension p to 0. And many kinematic results about these higher dimensional defects continue to be valid when we make this extension to be equal to 0. So this defect viewpoint follows both from the brane geometry and from the symmetry kinematics. So I guess it's not hard for you to agree that the giant gravitons can be viewed as defect, but the real question is, what is this defect picture really buying us? So I'm going to show in this talk that there are 3 main payoffs. The first one is computation. First of all, computing holograph correlators can be a bit complicated. In fact, that was a complicated problem difficult problem for many years. But in recent years, the computation of these correlators have been greatly streamlined by using the bootstrap strategy. So the idea is to fix directly these correlators using symmetries and the consistency conditions. And more recently, the bootstrap strategy has also been extended to CFTs with ordinary higher dimensional defects. So here, by viewing these giant gravitons as zero-dimensional defects will allow us to readily use these technologies which have already been developed. Second, this defect perspective will allow us to uncover certain hidden structures which are otherwise difficult to recognize. So I'm going to show in this talk, once we write everything in the defect variables, a hidden 10-dimensional symmetry becomes manifest. And this happens both at strong coupling and also at weak coupling. Finally, this defect language is not limited to giant gravitons. I will also show you that it provides a natural description for general light-light heavy correlators. So the defect perspective is not just natural, but it is also computationally useful. Good, so let me now define the basic objects. So for the light operators, we have the usual half BPS single trace operators. And the heavy operator is a determinant. And here, this variable t here is a 6-dimensional null vector, and it tracks the asymmetry polarization. For the space-time dependence x, we can place it on the same footing as t by also uplifting it into 6 dimensions. So this defines this null vector p here that lives in the 6-dimensional embedding space. The defect correlators are defined by simply taking the ratio, where we divide by the heavy operator 2-point function. Doing so removes the explicit dependence on the quantum numbers of the heavy operators, and this agrees with how we usually think about defect correlators. And here at the convention, I will always choose to put my heavy operators at 0.3 and 0.4. Very importantly, in this defect description, the heavy operators now only enter via projectors. So there will be 2 projectors, one for space-time and one for asymmetry. And they're constructed out of embedding vectors P3, P4, and the asymmetry vectors T3 and T4. So here I define the asymmetry projector slightly in a different way by adding this additional 1 minus, but as a definition, this is completely equivalent. It just projects to the orthogonal space, and I'm using this definition mainly for later convenience. Now constructing correlators becomes straightforward because symmetry is linearized. So we are allowed to only use the vectors from the light operators, and for the heavy ones, we are only allowed to use their projectors. It's not difficult to convince yourself that the defect 1-point function is completely fixed up to a constant. And if you write things out explicitly, this is just the ratio of 3-point and heavy 2-point. So it agrees with this ratio definition I showed you in the previous slide. 2-point functions, on the other hand, are not fixed because they're invariant cross ratios. And we also expect these cross ratios from the 4-point function perspective. In fact, we can use the same cross ratios in 4-point functions. So U and V are the standard conformal cross ratios, and sigma and tau are similarly defined for asymmetry variables. We also have more constraints coming from the fermionic generators, and they give you constraints in the form of superconformal word identities. So here the nice thing is that we do not need to redo the whole analysis because we can just recycle what has already been known for high BPS 4-point functions. So the role of these word identities is basically to let U, V, and sigma and tau to talk to each other. So more precisely, we need to do a change of variables to trade U and V for Z and Z bar, and similarly sigma and tau for alpha and alpha bar. So the statement is just once you set alpha bar to 1 over Z bar, your correlator becomes the meromorphic function independent of Z bar. Now, these word identities can also be solved in general, and the solution is the sum of 2 pieces. First, there's an inhomogeneous piece, which you can just take to be the free theory defect 2-point function. In the second piece, after you strip away some factors determined by superconformal symmetry, you can define this reduced correlator H, which contains all the dynamical information. And because of this factor, the quantum numbers of H are shifted, so the conformal dimensions are increased by 2, and the asymmetry charges are decreased by 2. In particular, if you look at the lowest allowed values for this case, which is 2, so that's a stress tensor multiplet, you find the reduced correlator is actually an asymmetry singlet, meaning it is independent of T. So that's as much as we can say just from symmetry alone. So let us now turn to the bulk description, where there is a defect effect theory given by supergravity. So very schematically, we can start from the D3 brane action. We integrate out S3, and that gives you a one-dimensional effective action. A more careful treatment also requires you to integrate over the moduli of the supergravity solution. Now you take this 1D action, and now you can expand in bulk and defect fluctuations. So here in each term, the first index corresponds to a number of defect fluctuations, and N is for bulk fluctuations. In particular, from this 2,0 term, you can read off the spectrum of the defect And these modes are organized into short multiplets of the preserved superconformal symmetry. The bulk spectrum, of course, is not affected because the distribuant does not back react to the geometry. And there are also infinitely many more terms, and these correspond to interaction vertices. So this tells you that in principle, these giant graviton correlators can be computed by brute force as the sum of diagrams. Explicitly at large n, these are the types of diagrams that gives you the leading connected contribution. So you have exchange diagrams both in the bulk and also along the defect. There are also contact diagrams. Of course, this diagrammatic procedure is straightforward. However, if you really wanted to implement this in practice, this is very cumbersome. So for example, it is highly non-trivial to extract all the needed vertices, and also keeping track of all the combinatorics is very tedious and prone to mistakes. So the better strategy is to bootstrap. And here, the key idea is to bypass the explicit details of the effective Lagrangian altogether. And we want to directly fix the correlators by using symmetries and the consistency conditions. And this algorithm can be described in 3 simple steps. So the first step is to write down an ansatz as the sum of all the possible diagrams, but with unfixed coefficients. And here for fixed external operators, the number of diagrams is actually finite, and the fields that can be exchanged are also determined by group theory selection rules. The second step is to evaluate this ansatz, and here a very nice feature is that all these exchange diagrams can be expressed as finite sums of these contact diagrams. The contact diagrams can be evaluated in a closed form as an F1 function, which further simplifies to just logs and rational functions for our case. So after doing this, the ansatz is just an elementary function of the cross ratios. The last step is to impose the superconformal word identities, and let me remind you, it's just a statement that the twisted correlator is the meromorphic function. So we can turn that statement into a set of overdetermined linear equations for these unknowns that we have put in the ansatz. And then we just solve these linear equations, then we fix all these coefficients. So in this way, the bootstrap allows you to efficiently compute any 2-point function. And here I'm just showing you the simplest example where K1 and K2 are 2, so that's the stress tensor multiplet. So as you can see, the free piece is just a simple rational function. The reduced correlator contains just a single power of log V. And this is actually much simpler to the case of 4-point functions of these operators, where you have this more complicated building block of D functions. We can also go to higher values of K1 and K2. The correlators are similar in structure, but lengthier in expressions. And we also did a number of consistency checks. So for the free piece, we checked that it agrees with the direct calculation of free theory. We also extracted 1-point functions, and they agree with the direct supergravity calculation. Finally, for this 2-2 correlator, where we have localization data, we also computed the integrated correlator, and we found the numbers match. So it turns out that these giant graviton correlators have an interesting higher dimensional structure. But before I show you that, let me first mention a similar known story, which is hidden symmetry in the case of 4-point functions of these light single trace operators. So the story there is that there is a generating function for all these different 4-point functions, and the 4-point function can be obtained by uplifting the simplest lowest weight 4-point function from 4D to 10D. So at a more technical level, what we are required to do is to group together the embedding space vector P and the asymmetry position T to get a 12-dimensional null vector that lives in the embedding space of R10. And then we look at the simplest correlator with lowest weight, which is an asymmetry singlet. So that means it only depends on xij squared, or equivalently pi.pj. So the uplift requires us to replace these inner products of p's by the inner product of z's, and this introduces t dependence and gives you a generating function. Now you just need to tailor expand in C, and you can recover all the higher ones. I should mention that there actually isn't a precise understanding for why this happens, but there's an intuitive picture. So the picture is that we can do some sort of wild transform to map ADS phi times S phi to flat R10, and in a certain sense, all these different 4-point functions become a single amplitude intending. Now you may want to apply this prescription to these giant graviton correlators by viewing them as 4-point functions. But you find that this naive attempt fails, and it fails because in the last step, when you do the Taylor expansion, you also change the charges of the heavy operators. But we are supposed to keep the heavy operators fixed. Nevertheless, there is a generating function for these giant graviton correlators, and to get that, we need to use a different prescription. So in the new prescription, the part where we replace P by Z is the same for the light ones. But for the heavy operators, because only their projectors show up, what we should do is to uplift only their projectors rather than their underlying vectors. So more precisely, we also start from the lowest weight correlator, H22. It's only a function of x, so only the space-time part of this projector n appears. Now in the uplifting, we want to replace this n by the combination of n plus m, where m is for R symmetry. And this turns out to give you the correct generating function, which you can Taylor expand again and get all the other 2-point functions. Also going back to this picture of wild transform, this combination of n plus n also makes sense because it projects to this 4-dimensional subspace, which corresponds to the Ward volume of D3. So here we're seeing this defect perspective is not just natural, but it's also necessary. It is necessary because this 10-dimensional hidden symmetry is now partially broken. So we discovered this symmetry at strong coupling, but the same structure also turns out to persist at weak coupling. The only difference here is that this structure no longer packages the whole correlators. Instead, it packages certain integrands of different KK correlators. And these integrands are defined by the Lagrangian insertion method. So we explicitly check this at 1 and 2 loops, but we believe this structure should persist to arbitrary loops in perturbation theory. Let me also mention that there is also a similar story that was previously observed for correlation functions of all light operators. Now, from these giant graviton correlators, you can also extract a lot of data. For example, in the defect OP channel, you will find operators made out of a giant graviton and a light supergravity mode. Such operators, they have enormous dimensions, which correspond to the binding energies of such a bound state in ADS. Now, there's some technical operator mixing problem you need to solve in order to extract these enormous dimensions, but this problem can be solved by using all the KK correlators we've computed. And here, the hidden symmetry again plays a useful role. More precisely, this partially broken hierarchy structure tells us that we should use this 10-dimensional defect conformal blocks to decompose the correlators. And if you use these blocks, you find this mixing problem I mentioned gets automatically diagonalized. It also leads you to some useful differential operator with nice properties. I will not mention this in detail, but you can use this operator to greatly simplify the computation of quantum corrections coming from ADS loops. Let me end now with a broader lesson, which is this defect language is not limited to just giant gravitons. So consider a general light, heavy 4-point function. You might be tempted to say that in the heavy limit, this 4-point function simply reduces to a defect 2-point function. But this is a bit too naive because of order of limits issues. In fact, you can just check the giant graviton correlators. They are not reproduced from the single trace 4-point functions. The correct statement is instead block level. So in the infinitely heavy limit, we can prove that the ordinary conformal blocks for 4-point functions reduce to the conformal blocks for defects, to defect conformal blocks. And this happens both in the bulk channel and in the defect channel. So this gives us a general block level lesson. Namely, in the heavy limit, all light, heavy correlators can be decomposed into these defect conformal blocks. And this is completely kinematic and non-perturbative. We can also further exploit this kinematic fact and develop a defect version of the so-called analytic functionals, which will then lead us to non-perturbative sum rules for these light heavy correlators. Finally, let me conclude by mentioning a few natural feature iterations. So these include non-maximal and dual giants, quantum and string equations, and of course you can go to other backgrounds such as 87 times S4. There's also a lot to explore in the general analytic conformal bootstrap for these light heavy correlators from this defect perspective. So let me stop here and thank you very much.
Thank you very much. Questions, Shinan?
Very nice talk. I want to put one more future direction on this list. I think you could also compute this defect contribution to entanglement entropy, which is holographic due to this word line cross this RT surface. They should match with each other.
Yeah, thanks for the comment.
And also, I think one interesting question is, what is the G function in this zero-dimensional defect?
That I don't have an answer to, yeah. So, yeah.
It looks like some log of 2-point function of this D. But
could it be, yeah.
Okay.
More questions?
Just want to ask about this structure that you mentioned, this hidden 10-dimensional symmetry. So is it understood now whether this is some structure that holds beyond the leading larger limit, top limit, or this is something that's going to be modified? If modified, how that's going to change your some of the future direction discussed over here?
Yeah, thanks for the question. So people have also looked at this at like one loop level. So it turned out like this structure allows you to fix like most part of the correlator, but not all of it. So it seems to be like sort of gets broken by 1/n corrections. Yeah.
So there's is working based on the assumption, and then people find some contradictions.
So you can also compute these loop corrections by this bootstrap strategy. So you know how to compute the answer. And then you find like part of it is predicted by this extension of this hidden structure to loop levels, but it also gets broken, yeah.
Thank you.
Okay, there's one question out there.
So can we say anything about 4 heavy operators?
Yeah, that's actually, so I mentioned here also as a future thing you can do. So now you have sort of like 2 geodesic lines interacting with each other. Yeah.
Okay.
All right, so we are now time for the coffee break. So let's thank Shinan again. And we come back caffeinated at 11.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, welcome back. And this is the final talk of the day today. At the end of the talk, there'll be an announcement. So please wait after all the questions for the announcement. So we'll have a review talk on amplitudes for gravity by Clifford from Caltech.
Great, can you hear me? Okay, perfect. So first, before I start, let me thank the organizers and our very gracious hosts for what's been a fantastic and thought-provoking conference. It's a pleasure and an honor to be here. Today, my task is to report on recent progress in scattering amplitudes. I think were it maybe, 10, 20 years ago, this would have been a very simple task when amplitudes was just about computing perturbative amplitudes, most likely for collider physics or some kind of observation. As of late, it's become more complex as this field has kind of diffused outward and connected with adjacent fields. There's, of course, the usual linkages, usual connections to kind of phenomenology, string theory, collider physics, but there are now new points of contact with fields like cosmology, gravitational wave physics, fluid dynamics, and even some aspects of pure math. So as you can imagine, it would be essentially impossible for me to kind of summarize this isotropic outward moving progress. So I won't be able to do that. I won't be able to do justice to that work. But that said, before I get into the kind of technical substance of my talk, let me briefly not do justice to a couple developments in the last few years that have received a fair amount of attention. One is a long-standing program to kind of geometrize scattering, to think of amplitudes as volumes in kind of an abstract or auxiliary space. This, I think at its onset, was really about n equals to 4 superangles, but in the last few years, this is extended, this is generalized. It's now something which we can do for theories like phi cube theory, non-supersymmetric Yang-Mills theory, the nonlinear sigma model. It also includes tree level all the way to all loops, all orders in perturbation theory, as well as including kind of the analog of alpha prime stringy corrections to those theories. There's also been some work extending these ideas to cosmology. Something called the cosmological bootstrap is centered on basically taking the workflow of what's been learned in flat space for the S-matrix bootstrap and essentially trying to port those lessons into cosmology. Of course, doesn't answer any of the really big questions about what the true observables are in an eternal de Sitter universe. Really, they're just asking questions about, say, in correlation functions that our experimental colleagues actually care about, and their analytic structures and how you actually build them if you didn't have at your disposal things like Lagrangians or Hamiltonians. There's a lot of interesting work here that I also will not talk really about at all. And last but not least, there's kind of the elephant in the room, which is AI and machine learning, where all I want to say is that scattering amplitudes in particular is kind of a very fertile ground for something to happen simply because there's a lot of theoretical data. This was kind of alluded to in Andy's talk, where he mentioned that just tons of things have been computed, and I think while it's early on, there is some potential here. Again, I won't say much more at all more about that. For my talk today, I wanted to kind of focus some of the attention on amplitudes and its interface just with gravity, and my talk will split between classical and quantum gravity. For classical gravity, I really just mean classical gravitation as per MTW, and I want to tell you about something that's happened in, say, the last 6 or 7 years or so, which is an application of a battery of modern tools from high-energy physics to a decades-old problem in gravitation, which is the binary black hole in-spiral. So the in-spiral problem is just the question of if you have two black holes or two neutron stars in orbit, what happens to them? Okay, it's an ancient question. It's purely classical. It, of course, lacks many of the subtle issues that many in this room care about, and that's fine. But it's still a question that certainly observation cares about. I'll tell you about how there's kind of a wonderfully vertical integration of ideas here, where things that have a true lineage within string theory, things like the double copy, which emerged from fundamentally from the closed open string dualities, things like generalized unitarity, which were developed to understand supergravity, and also just methods from collider physics have all been kind of fused and merged in a way to give new results and teach us a little bit something new about perturbative effective field theory of gravity. Now, of course, the first thing you should think is, well, how could we say anything with amplitudes about this? A black hole merger is an extremely complicated, violent process, and I won't have anything interesting to say about the merger, the most interesting region. But this early in-spiral period is famously weakly coupled and perturbative, and that's where kind of all the action will happen, at least for this talk. There are many expansion parameters you can think of for two bodies interacting. They could be slow, they could be far apart, where the distance between them is large compared to their Schwarzschild radii. And then there's slow and far apart, which is the famous post-Newtonian approximation. So for the purposes of this talk, I'll be interested in this post-Minkowskian expansion, at least for this classical gravity part. And it's not for mysterious, it's not really mysterious, it's just because the kind of natural order parameter is g Newton, which we would otherwise call just perturbation theory. Okay, so we're doing perturbation theory in G. Now there's a definitive best way to compute in perturbative gravity, which I think everyone will agree with, which is to not compute in perturbative gravity. You shouldn't. You should instead compute in gauge theory and square it using now well-known relations which relate on-shell flat space scattering amplitudes in gauge theory to those in gravity. As I said, this was originally discovered in the form of KLT, but the kind of modern field theoretic version of it is called BCJ, and the kind of reason it's powerful is that it naturally feeds into loops, okay, which will be important. And I'll just mention briefly that this is not like a duality in any kind of standard sense. It's just a relationship between weak coupling objects, which happen to be amplitudes. The kind of simplest version of this, which is very familiar, is the 3-point amplitude. So if you look at the Yang-Mills 3-point amplitude on shell, this is the expression for it. It has a color structure constant as kinematics. The operation of color to the kinematics simply says to take the color structures and replace them with kinematics, and in doing so you get a new function that turns out to be the graviton on shell amplitude at 3-point. Okay. What's nice is that this generalizes beyond 3-point to n-point. For 4-point, this is the kind of next to simplest example. You take the Yang-Mills amplitude, you decompose it into its color structures and its kinematic structures. As expected, the color structure satisfied the Jacobi identity, perhaps less obviously. The kinematics, that is to say the numerator functions, ns, nt, and nu, also satisfy the same Jacobi identities. And that's a little more surprising, just because these are functions of actual momenta and polarizations. Okay. So the kind of leap here is to embrace that apparent, I don't want to call it duality, but that apparent isomorphism, and then take the color and replace it with the kinematics. So what happens if you take these CS, CT, and CU and replace it with other copies? Well, as you can expect, what you get is the 4-point graviton amplitude, which by kind of more conventional, Feynman diagrammatic means is extremely complicated and not worth doing in that old way. So this is a very old story. It's actually a pattern of so-called double copies which extend beyond gauge theory and gravity. It's also true for the theory of pions, which by this I mean the nonlinear sigma model, the chiral limit of chi-pt, where you can take two pion amplitudes, n-point pion amplitudes. You can take their flavor structures and strip them away in precisely the way I mentioned, and take products of their kinematics. And you get amplitudes in a theory called the Galilean, which is essentially the longitudinal mode for massive gravity theories. It shows up in kind of exotic theories of cosmology. You can do something similar with gluons and pions, giving you familiar connections with Born-Infeld theory, which of course we see all the time in strings. And there's many others. The kind of point here is that it's kind of ubiquitous. It's a proven fact at endpoint tree level, and it's been recycled into loops using unitarity methods. There's a whole multiplication table of these theories. If you have a theory that you like very much, there's like a decent chance it's on one side or the other side of this type of squaring relation. I won't talk much more about that here. Now, kind of returning to the original question of how this could be applied to, honest-to-goodness Einstein gravity black holes, there are some immediate challenges that you'd see. Well, you'd say, well, this is great, gravitons are nice, but black holes are not gravitons. On top of that, the in-spiral itself, an orbit of two bodies, is almost as far as you can imagine from being a scattering amplitude. And last but not least, you probably heard the most power we have in amplitudes is about supersymmetric theories or maximally supersymmetric theories, and Einstein gravity, of course, is not that. But nevertheless, these are all not problems. They're easily surmounted. There's a ton of technical detail that I just will not go into here, but let me just tell you the kind of basic workflow for this kind of procedure so you get a sense of what folks have been doing. In the first few calculations of this type, we started with gluon scattering amplitudes. These are things that have been computed for decades using methodology from collider physics. We double copied them to 8 gravitons. That's the straightforward part. Then we want to relate these to black holes. Now, of course, if these were large, fluffy black holes near their merger, this would fail. The point is that when they're far away, we can think of them as essentially point particles that are massive interacting gravitationally. And here, we just need to build a scattering amplitude for massive bodies interacting through gravity. In this case, we take those graviton amplitudes we built, and through various tricks, for instance, Kaluza-Klein reducing them to get massive bodies interacting with gravitons, and other tricks which include gluing them together using unitarity, we can build up the scattering amplitude for 2 massive bodies. Okay, so I'm saying the words black hole, but it's actually something much simpler, which is just, if you like, point particle masses. We can add interesting features like tidal moments and finite size effects that can all be included if you would care about, say, neutron stars. But the point is, this is an effective field theory type calculation. Still, it's not at the level where it connects with an orbit, and then we use, again, decades-old methods developed for heavy quark effective field theory, non-relativistic QED and QCD, where you take amplitudes and you match them on shell to a Hamiltonian. Okay, very straightforward. It lets you extract from this vertical integration of calculations, the Hamiltonian for 2 black holes in binary in-spiral to various orders. Okay, so that's one of the objects that's kind of more palatable to our friends at LIGO who actually care about these calculations. Now, as I said, I'm not going to review like any of the inside details. I think it would not be particularly illuminating to you. But just to give you a sense of where things have gone and where they started, maybe an imperfect metric is just what we have learned about the black hole binary Hamiltonian, the Hamiltonian governing 2 black holes in spiral for the conservative dynamics, let's say. This is something, as I said, is a perturbation expansion in g Newton and in the relative velocity of the 2 bodies. This, of course, is like an ancient field. So, the post-Newtonian expansion was initiated at 0 pn by Sir Isaac Newton, 1686. 1938 was Einstein, Ilford, and Hoffman. And then there's a sequence of tour de force calculations by giants like Thibaut de Moor and Luc Blanchet, who basically just founded this field and have been doing this for decades. As I mentioned, the kind of perturbative expansion that's natural from our point of view is powers in g Newton. So we naturally cut across this diagram. So for any given power of g Newton, we extract all powers of velocity to infinity. It's complementary, obviously. When we started thinking about this in 2018, we made slow progress, but it's moved on from 2019, 21, and 2025. Progress has happened. It continues. This is now kind of a whole cottage industry of folks computing things, including the conservative dynamics, radiation, waveforms, and tidal effects. I, again, won't be able to do justice to any of these interesting developments, but one kind of key point is that there is interplay here with the folks at LIGO who actually build the waveforms. Okay, they have been directly encouraging and asking for these types of calculations. It remains to be seen how useful they will be eventually in searches, but it's something that I think is some progress. That's really all I want to say about the kind of classical gravity story, just to give you a lay of the land of what's known and what's new. At this point, I'm going to switch gears and talk about a completely different question, which will be actually more of the bulk of my talk, which is about the connection to quantum gravity. Okay, so this is now a question about quantum mechanics and general relativity. And as you can imagine, it's very natural from a kind of bootstrap approach. The analytic S-matrix program of old had this very ambitious goal of building everything from kind of first principles, conservative principles. Here the principles are quantum mechanics and general relativity, and the question is, what is the space of consistent ultraviolet completions of general relativity? Now, as you can imagine, that's a high bar. Quantum mechanics and general relativity will not be enough to specify what the theory is, kind of clearly, but I'll tell you how a number of approaches, which are very different in nature, Some are analytical, some are numerical, they use methods of a very different character, are all kind of, I don't want to say converging, but orbiting around amplitudes that are stringy. Okay? It appears to be that there is something special about these functions that we all know and love. So I want to tell you about that here. Now, before jumping into quantum mechanics and general relativity, just to remind you, this very same bootstrap idea works very well when you have quantum mechanics and special relativity. Okay, so famously, if I just tell you I have a Poincare invariant theory, and I ask what are the allowed 3-point amplitudes in that theory, you can classify them. In particular, you could ask what is the space of 3-point amplitudes for a massless spin 1 particle that interacts with itself. And you learn in kind of an oblique way about gauge theory. You construct the f squared and f cubed higher dimension operators via Yang-Mills theory. This is a way of like deriving gauge theory. Similarly, for the graviton, you can ask the question, if I have a massless spin 2 particle and it self-interacts, what are the allowed operators? And it's the usual Einstein-Hilbert quadratic curvature and cubic curvature type interactions. This is, of course, a very familiar story. And it's really nothing more than classifying effective field theory operators. It's just doing it in kind of a oblique way. Those examples were examples where we have a Lagrangian. You can see that the power will be where we don't have a Lagrangian, and it's just more mysterious what the theory space is, which is why this is a very natural approach. This approach generalizes past 3-point. Famously, BCFW, Brito, Cacciazzo, Feng, and Witten show that you can use essentially factorization and lower point to build all endpoint. So the idea is that this essentially lets you construct the full effective field theory. BCFW also famously has so-called boundary terms that are ambiguous, and from an effective field theory viewpoint, we should think of these as essentially Wilson coefficients that could be free, unfixed Wilson coefficients. So again, there's nothing new here, there's no free lunch, it's just effective field theory. Our ignorance is always embedded inside some set of Wilson coefficients whose values we don't know unless we assume more. Okay. And these are effective field theory, so we don't know what the ultraviolet is yet. Okay. Now, this leads me to the question that I'm very much interested in, which I think is maybe one of the important questions in high energy theory, which is, what is the high energy theory? If you just keep extrapolating to higher and higher energies, what do you get? Here we can take a lesson of what the additional ingredient is. It's kind of obvious. It must be unitarity. We already saw this at the Large Hadron Collider. Before the discovery of the Higgs boson, if you thought about the electroweak model and just scattered longitudinal W bosons, you would have seen immediately that it violates perturbative unitarity, which is already a sign that something was breaking down, something was off. Once the theory goes nonlinear, it has infinite numbers of counterterms and becomes unpredictive. Okay, so we already had this sign, certainly for weakly coupled theories, that something had to show up, and of course that was the Higgs boson. The precise similar analogous logic applies to graviton scattering, where we imagine scattering at higher energies. Here, we want to kind of be at the Planck scale but not exceed it. If we exceed the Planck scale, we actually know what the theory is. It's a black hole that's formed. We're kind of precisely interested in the regime below the Planck scale where general relativity is breaking down, and we want to understand what replaces it. One option is a set of higher spin states with a particular set of masses that go as square root of n. But the question is, how do we learn that? Or is that generally true? That's our question. So clearly the extra input is unitarity in these cases. These examples are framed perfectly in the language of amplitude. So it's a very kind of a natural approach to take here. The key players here, as you can imagine, are the Veneziano and the Virasoro-Shapiro amplitudes. Here I should apologize that I'm going to be kind of stripping away freedoms of Reggie intercepts, setting Reggie slips to 1, and also prefactors that might be in the more familiar formulas. But for these functions, this is essentially the kind of target objects if you wanted to bootstrap strings. And I'll also just mention historically, as you all know, that the way that the Veneziano amplitude was discovered was through such a bootstrap. Okay? It was not a theory of strings originally. It was meant to be a phenomenological model of the hadrons. I would say also to its credit, and I view this actually as a positive, Veneziano in its inception was meant to be a description of the strong interactions. And like any great theory that makes predictions then is testable, it was ruled out. There was deep inelastic scattering. It wasn't this. It was instead QCD. And that, I think, is an immense success. And that's why it's predictive. The analog of this in the gravitational case is the Virasoro-Shapiro amplitude. Okay, now what properties do these functions have? What properties do these functions have that make them special? I want to ask, what mathematical features do they have that we could use as an input for a bootstrap? And as is well known, they have a number of properties that all seem miraculous independently. The first is that they have an infinite tower of spins. Okay, famously, if you have an EFT of just even one single higher spin object, it's very difficult to make that self-consistent. But string theory takes an infinite tower of them and makes them all consistent together. Second is the feature of high energy softness. Okay, and occasionally I'll mean softness in the Reggie limit, sometimes in the hard scattering limit. I'll try to make that clear when I get into the details. But the point is, its UV is better, just simply better, than what you expect or could ever imagine in a quantum field theory. I view this as the most important feature of strings in terms of UV completion. If your UV completion had worse high energy behavior, it wouldn't be very good as a UV completion. So I view this as kind of very central. Another element which has also been spoken about a bit at this conference is the property of dual resonance, which is this picture from the textbooks where you can take the amplitude and extend it in either of two channels. So write it not as a sum of channels, but in either. As we'll see in a second, these are actually not all linearly independent. And this is the question. If you take these separate assumptions and you ask, write down the space of functions that have these properties, is the unique solution inside string theory, or is there something separate? Okay. Here are the kind of most conservative assumptions I'll start with. And again, I'll be reviewing multiple other groups' work, but I think across the board we kind of stand by these basic conservative assumptions. We'll be working in flat space. We have Poincare symmetry. We'll be assuming an S matrix, which is analytic. We'll have crossing symmetry, which, depending on whether it's a planar or non-planar amplitude, will imply various symmetries of exchanging kinematics. There is the constraint of unitarity, which I've written here as the constraint of nonlinear unitarity on partial wave coefficients. Occasionally, I'll be sloppy and just talk about something called positivity, which is the statement that the imaginary part of this AL is non-negative. I'll try to, again, also make it clear when that assumption is being made. And then last but not least, the statement of polynomial boundedness. Okay, so these are just input assumptions, and we'll kind of tweak and change them as we go. If I were to draw a map of the kind of approaches here, they bifurcate on two axes. There is, of course, analytical, pen and paper, and then there's numerical, which is, of course, deeply enriched by having computers nowadays. There's also another kind of conceptual division, which is between ruling in and ruling out. And hopefully it's obvious what I mean, but let me explain. If I give you some set of assumptions, you could rule out a theory in the following way. You could be handed an amplitude or be handed a Wilson coefficient and show that it's inconsistent with that set of assumptions, and that rigorously rules it out. Okay. There's a converse approach, which is to find a function and rule it in. That is to say, take some set of assumptions, build a function that satisfies those properties. But I wanted to emphasize that that is a little kind of logically fraught in the sense that it doesn't technically rule anything in. If you find a function that satisfies your bootstrap constraints, it doesn't mean it's a consistent theory. It doesn't mean that anything other than it satisfied your constraints. And furthermore, if you fail to rule something in, it doesn't rule it out because you may just have not been clever enough. Okay. Now, there's a lot of work. I've just listed a couple of the kind of original papers here, but they kind of go under these names. Again, this is a little broad here, which I'll talk about shortly. The kind of original positivity you may have remember from the papers by Alan Adams and Nima Arkani Hamed, where they bound signs of Wilson coefficients. I'd put kind of squarely in the zone of analytically ruling out. The idea here is that you write a Wilson coefficient dispersively in terms of some positive sum, and you can argue that it can't be negative. Okay, that's a very familiar old story. That has been now, I'm sure you've also heard, extended into a broader class of bounds called the EFT-hedron and moments and arcs. These are all things I think you've heard about in previous strings, so I won't talk about them. I'm going to focus more actually on some of these numerical type bootstraps first. Null constraints, primal bootstrap, and then analytic type deformations. One thing I do want to mention about analytics is that it actually is kind of secretly both rows of this, and I mean you'll see what I mean shortly. If I give you some set of assumptions and I can solve the problem entirely, if I can solve that analytic problem, then you've actually ruled in and ruled out at the same time, because you know the space of functions that are ruled in, and every function that's not that function is ruled out. So once you have sufficient analytic control, you can actually take on both rows at the same time. Okay, with that said, let me tell you about null constraints. And again, there's tons of detail here and great papers that go into this, but I want to give you the kind of essence of what is assumed and what comes out. The basic idea of a null constraint is to take the amplitude and write it dispersively in terms of its imaginary part. So this is just a dispersion relation for the amplitude A of s comma t. The input assumptions are here shown on the right. It's analyticity because we use the dispersion relation. It's UV bounded because there was a boundary term which we discarded. And it's positivity because we'll assume that this discontinuity, this imaginary part, is non-negative. Okay? That's, if you like, just the positivity bound I mentioned before, not full nonlinear unitarity. So that's the setup. Okay? You can compute, if you like, there's an abstract representation of the amplitude in terms of some unknown positive objects on the right-hand side. The logic of this is to use crossing afterwards. Okay? So if you took the crossing symmetry afterwards, and this gives you a bound on the allowed Wilson coefficients that can appear. Okay? There's many variations of this, but let me tell you the one that's maybe the most relevant to this particular question. A set of very beautiful papers by Leonardo Rastelli, where he does the following. He assumes what I said, points 1 and 2, which is the null constraint. He then continues to move on to assume the case of d equals 10, tree level, so 4-point tree level, 10-dimensional amplitude, with maximal supersymmetry and non-planar, okay, and builds that function. And what you're seeing here is two axes, which are two Wilson coefficients. And what he finds is this kind of string theory region embedded nicely inside an allowed peninsula. Okay, so the kind of key point here is that what's being constrained is a particular set of Wilson coefficients that correspond to the Virasoro-Shapiro amplitude. And it's not cornered. Okay, so of course the dream here is always to like land on a corner, like as in the Ising model and the conformal bootstrap. It's not quite happening here, but nevertheless, it's kind of interesting that it resides in such a prominent fashion here. This is a relatively old story. They did this for type 2 and more recently for the heterotic string. Very interesting set of papers. This has been kind of pursued with an extra ingredient in the last year to get more mileage. This is a paper by Henrietta Elvang and her group, where they consider a slightly different setup, but still, as you can imagine, pointing to strings. I'll explain what I mean by that. It's a null constraint, so it's still bullet points 1 and 2. Here they study d equals to 4 tree level maximal SUSY, so n equals to 4 superring mills in the planar limit. And they have an extra ingredient. The extra ingredient is higher point factorization. The kind of broad picture is that the constraints of supersymmetry together with higher point factorization actually impose constraints on 4-point, which are highly non-trivial, and in fact imply the monodromy relations. With this extra input, it reduces the island to this green strip, this very small green strip that you maybe not even be able to see, and it corners, for Veneziano, its Wilson coefficients. This is, I think, very enticing. It depends on maybe your priors, how surprising it is that if we assume maximal supersymmetry, the only way to UV complete n equals to 4 is Veneziano. It may be obvious or non-trivial, depending on who you are. But I think it's very interesting. One thing I do want to mention, though, is that when we say these theories are being cornered, we're not constructing the full function, the full Veneziano function. This is essentially the series expansion of Veneziano at some low order, and there's some interesting fact that these there's uniqueness in those Wilson coefficients. They can go, of course, attempt to go higher. That's a very interesting question, but this is extremely intriguing, and I think not a coincidence. Okay, another direction which I think is also very fascinating is this other path of, rather than rigorously ruling out, just trying to find a function that actually satisfies your conditions. This is called the primal bootstrap, and it's very devious. It starts with different assumptions and imposes different assumptions afterwards. What it assumes first is crossing symmetry, so they write, if you like, just an ansatz, an STU crossing symmetric ansatz. They write it in terms of a variable which manifests analyticity. Essentially, it puts the branch cut in precisely the right place. And it also enforces UV boundedness. Okay, so their ansatz has these two input, and then at the very end, they compute partial waves and then write down a semi-definite programming a problem to solve for that inequality. Okay, it's quite devious. What have they found? Again, much more has happened than this work from 2021. But in this really interesting paper, what they showed was that if you write down a function, which is, if you like, nominally non-perturbative, and what I really mean by that is there's no assumption of simple poles or a meromorphic function, has all those nasty branch cuts. If you study that object and impose nonlinear unitarity, working in 10 dimensions with maximal SUSY non-planar, many inputs, but then you ask to extremize the R to the fourth coefficient, so minimize R to the fourth, then they again find some confluence with the prediction of type 2b strings at the self-dual point. So it's, again, something which definitely doesn't seem like an accident. It doesn't rule it in as this being that string amplitude. These objects have kind of peculiar properties, but it's really interesting, I would say. Okay, now that's what I wanted to say about numerics. I wanted to shift slight gears to talk about analytics, because I wanted to argue that you can actually learn something just by thinking about the functions themselves. Already this was pointed out by Simone Caron-Roy when he wrote down the actual null constraints, which is that they tend to be poisoned by certain analytic functions that we can understand, and at least we have a strong suspicion aren't real physical theories. Okay, and these correspond to theories with infinite spin states, and let me tell you what I mean by that. Okay, so if you look at these null constraints, they often have cusps, or kind of corner points, which are objects like this. This is not a typo, it's not a sum of STU poles, it's a product. This object is polynomially bounded positive. It satisfies positivity of the imaginary part of partial waves, Lorentz invariant and crossing symmetric. It has one peculiar feature, which is that it corresponds to an infinite spin state at a given resonance. You can see this by just extracting the residue at s equals m squared. Just sit on that pole, you pull out a residue. That residue is not a polynomial in T, which means it's not a polynomial in cosine theta, which means it's infinite powers in cosine theta, which is infinite spin. You could think of this as like a macroscopic object that's being exchanged like in a narrow resonance. It's odd. At present, well, we have reasons to think this would be inconsistent because of the covariant entropy bound, trying to couple it to gravity, the density of states is infinite. There's many confusions about this. I don't know of a rigorous S-matrix argument to rule it out, but for the purposes of this talk, we'll just avoid these objects. So at any given resonance, we want a finite spin object, not an infinite spin object. Let's take that as an input, just as an assumption. A second thing to keep in mind is how important the ultraviolet is. I had already mentioned this before, it's crucial. It's kind of instrumental in all these dispersion relations because if we take, for instance, a planar amplitude and write it dispersively, here I fix T, so there's poles in the S channel, and we don't hit the poles in the T channel because we fix T. We have these boundary terms and with some discontinuity. And for the very simple case of tree-level meromorphic amplitudes, which is what I'll focus on here, this discontinuity is just a sum of residues in the S channel. And we have some boundary term here, A infinity. This is the type of term that we throw out because of polynomial boundedness and so on. But kind of a lot of the magic is in how rigorously you can throw out this term. One thing I'll mention, which is I think worth noting, but to the experts of course obvious, is that this is precisely related to the statement of dual resonance. Okay? What do I mean by that? Well, if you can fix T and expand your amplitude in the S channel, then of course you can do the same in the T channel. And that's precisely the statement that the softened UV behavior that you need to even write down a dispersion relation that's unsubtracted is precisely the statement of dual resonance. Okay, these are linked to each other. So this kind of stringy picture we have of stretching the world sheet can be, if you like, just restated as a fact about unsubtracted dispersion relations. Okay. Now, given everything I just said, Lorentz invariant, analyticity, unitarity, crossing, those conditions I mentioned, there's still just a whole zoo of possible functions, analytic functions you can write down that satisfy all those conditions. Perhaps all of those are putative UV completions of of the world. Many of these have an ancient lineage, a set of amplitudes called the Kuhn amplitude, written down as far back as 1969, around the same time as the kind of dual resonant model craze. It was kind of soon forgotten because string theory became what it is now. There are models that David Gross wrote down, deforming the world sheet or summing satellites of amplitudes. This is a very old story. More recently, folks like myself have also just been building functions to see how much flexibility is there in this bootstrap. The kind of main takeaway is that there's many options, and importantly, these options do not all have the string spectrum. Some of them have very exotic spectra. Some of them have completely tunable spectra that you can hand us to give you an amplitude. And these are nice analytic forms. I personally do not believe any of those are consistent theories. I would view this as a clear example of a primal bootstrap telling you the limitations of your assumptions. Now, here's the question: what more would we assume to get string theory? Okay, like what implies string theory in terms of mathematical assumptions? And for this, I think we need to back up. Okay, so first, I want to just generalize. Okay, obviously, if we assume things like a spectrum of mass squareds that's linear and an integer, or if we assume there's a world sheet, or if we assume that the amplitude is made from gamma functions, that's a huge assumption. We want to assume as little as possible. So what we're going to do is just parameterize our ignorance as much as we can. So what I'll define here is some set of levels, some states labeled by n. Mu will be the spectrum of mass squared, which I don't know. J of n will be their spectrum of spins, and alpha of t will be the leading Regge trajectory. So the idea is, like, the goal here is to get these out of some set of conditions, not assume them. Now, there's already kind of a clue as to maybe what one of the extra ingredients is, which is garnered just by looking at kind of experimental data, examples of deformations. Consider the following exercise. So here I've shown you plots that correspond to deformed string amplitudes that David Gross wrote down and that Sasha Zhiboda wrote down a few years ago. Do the following exercise, okay? Take the amplitude and sit on a pole in that amplitude and extract the residue. The residue is a polynomial in t. Okay. Now take that polynomial and just plot its roots in t, like plot its t roots. Okay. If you do that at each level, you get some sequence of numbers that you can then plot. So this here is the level n. Now you can see that at kind of low n, it's a little chaotic. There's some kind of strange structure. But at sufficiently large n, that kind of very accumulates into kind of orderly fashion. Okay. This is an interesting feature. Why is this true? It turns out that there's a very simple explanation for this, which transcends string amplitudes. It's actually a feature of any scattering amplitude, which I want to explain now. Okay. Just an extra relationship, just to kind of spoil the end, it's a relationship between these residue zeros and the UV behavior of the amplitude. That's what the punchline will be. Let me show you how to derive it. It's actually very straightforward. As usual, there's caveats and details that I'm going to elide, but let me show you the broad picture. Take an amplitude and just compute an integral over a big circle, which we'll call C. As I said, we're thinking about a tree-level amplitude, so there's poles here on the axis that they have not shown. We just want to draw a circle that kind of avoids those poles. Okay? You could consider concentric circles that I'll call C prime and C double prime, and just think about these arc-type integrals. Now consider the case where these contours are asymptotically large. Okay? In other words, the radius of these arcs is huge. How huge? Precisely huge enough that I can use the Regge behavior as a good approximation to the amplitude. Okay? The Regge behavior is defined as the thing that the amplitude approaches, so move to that regime. So in this case, I can evaluate these integrals at least approximately up to subleading and 1 on S corrections, subleading and 1 on radius corrections this way, and you'll notice something interesting when alpha of t hits an integer. Okay, when alpha of t happens to be tuned to the value of an integer, these are simply monomials in S, which means they're completely analytic functions, and what that means is the branch cut has disappeared. Okay, that branch cut, if you like, was a proxy to the sequence of poles on the axis, and this thing has become analytic. What does that mean? Well, that means that if I use Cauchy theorem to write these integrals as sums of residues, they're all sums of residues, it means that these objects do not, well, they're all the same, which means that the residues that interleave these concentric circles must vanish. Okay? So the statement is, at sufficiently large n, where you're at the level where the theory is Reggeizing, When alpha of t is an integer, the residue has to have a vanishing, a zero. Okay? It dictates where those zeros are. You can see this kind of explicitly by just doing the integral, computing the residue. You find that the residue goes as sine pi alpha, which vanishes for integer values of alpha of t. Here there's a slight caveat I should mention, which is kind of important, which is that the zero could be canceled in principle. This is an amplitude, it has poles. It could have a pole in t precisely when there's a zero in t, and they could cancel, which is why we have to assume that we're safely below the gap to guarantee that the residue vanishes. So the ultimate claim is that for large n residues, where the theory is now regiized, for t below the gap, integer values of alpha of t cause the residue to be zero. This, if you like, is a postdiction for a very familiar feature you know from your textbook in string theory, which is the appearance of Pockhammer-like objects in string amplitudes, these kind of product factors, factorial type objects. Here for Veneziano, you see that the residue has a structure that's following entirely from the fact that the Reggie trajectory itself is linear. When alpha of t is equal to an integer below the gap, that's precisely explaining this structure. Okay? So of course, I'm not claiming that we're not going to assume this particular Veneziano amplitude, but the point is that this is a generic feature. Whenever you have a whole sequence of poles, the residues must vanish when they interleave these circles. So this now tells us kind of what we want to assume if we want to get strings. Like if that's your target, you could of course not assume these and get something different, but this is the question we're asking about. For reasons that I'll explain shortly, these two assumptions are sufficient to bootstrap the full functional form of the Veneziano amplitude, okay, analytically. The first assumption is we call ultrasoftness. I'll explain what it is, but it's essentially just a statement that the fall off of the amplitude, the Reggie behavior, is falling off as good as string theory. It's not the assumption that the Reggie behavior is linear, it's just the statement that it falls off very fast. I'll tell you what I mean by that. And second of all, something we call minimal zeros, which is, again, I can explain now that I've told you what these zeros are. Given some UV behavior, there are mandated zeros of the residues. I just showed you that. Of course, a residue could have those zeros and even more zeros. It could have a bunch of extra zeros that have nothing to do with anything I've said. That's completely fine and consistent. For that reason, we define something called minimal zeros, which is the minimally consistent amplitude. It's the residue that has the fewest number of zeros possible, but not fewer. Okay? What's nice about this construction is it gives a notion of a minimally consistent amplitude, a residue that has those zeros but not fewer. It's just an assumption you can use, and we'll see what comes out. The reason for the ultra-soft assumption was, you can see just from the usual shape of Reggie trajectories in quantum field theory and string theory. Quantum field theory famously does not allow for alpha of t to continue going off to minus infinity. It bottoms out. String theory amplitudes like the Veneziano amplitude go on forever. There's other exotic amplitudes I mentioned before, like the Kuhn amplitude or so-called Q-deformed amplitudes, which also kind of take a deep dive. I'm going to preclude them just because they're not ultra-soft, but I wanted to just mention that actually there's nothing actually strictly wrong with including this. What's actually important is that as these curves cross various integers, that there's an infinite number of crossings. Okay, so the quantum field theory line, you can see will have some number of crossings, but eventually will tap out. But the other cases go on forever. Okay, the reason why this is powerful is it tells you that there's an infinite number of constraints eventually. You go to sufficiently negative t, you'll get more and more constraints on the residues, and that's why it actually gets you some juice. Okay, so I also want to emphasize that at no point am I assuming a linear trajectory. Really, we're just assuming any trajectory that goes off to minus infinity as t goes to minus infinity. So just something which is bijective for negative t. So that's the precise statement of ultrasoftness, which is assume that the amplitude falls off infinitely at infinite momentum transfer. Okay, that is to say alpha as t goes to minus infinity goes to minus infinity, and assume minimal zeros, which says that the only zeros of the residue are at these points. Okay, that's the assumption. Turns out with these assumptions, you can bootstrap Veneziano. Here's how it works, okay? Let's write down an ansatz which has this property. Okay? As I said, all the residues have to share zeros as you build these curves, and they have to vanish for values of alpha t at an integer. Let me just parameterize those vanishings with a sequence I'll call CK. So this C sequence is parameterizing where those vanishings are, and it's unknown. There's also a mass spectrum, mu of n, which is also unknown, so I don't know what that spectrum is either. And then there's a residue normalization C of n, which is unknown too. Okay? But this is a general function that parameterizes that set of ansatz assumptions I mentioned previously. It's definitely restrictive. This is not everything, but I mean, in the sense of I could assume less and get more, but for the minimal zero and the ultra soft assumption, this is the answer. This object is not obviously anything familiar, but we can actually impose the last condition, which is crossing. So you'll note that this has implicitly just been written as an S-channel dispersion relation, so I didn't manifest crossing symmetry. But we can now impose crossing symmetry. And what you do is you evaluate this amplitude at these zero loci. Okay? And you just compute equations and solve for the sequences. What's interesting is that even though this is an infinite set of nonlinear algebraic equations, you can solve for this space analytically in closed form completely. I won't get into the details of how, but you can solve for the full space of solutions to this problem, and you get a 3-parameter space. An analytic space where mu, xi, and little c are defined in this kind of complicated way. Q, R, and W actually had origins in prior literature. Q is precisely the Q integer spectrum that I mentioned before. Theories with Q away from 1 have mass squareds that are Q integers. R and W, actually R was a parameter that Grant Remen and I wrote down in a set of so-called hypergeometric amplitudes that we wrote down a long time, a couple of years ago that we didn't know what to do with, but it showed up in this bootstrap. And W was a new parameter that was a new class of amplitudes. Now the key point is that if you look at this span of theories, there's only one point in the space which is ultra soft, and that's the point 1, 0, 0, which is precisely Veneziano. So the statement is, this is the workflow. Start with an amplitude, write a dispersive representation in the S channel, assume minimal zeros, which enforces the structure of the residue. It's a constrained structure, but one which still depends on infinite sets of sequences that are unknown. Enforce crossing. And then finally, this very good ultraviolet behavior is satisfied only by one of these amplitudes, which was precisely Veneziano. Okay, so this was the argument. We can, of course, ask about relaxing those assumptions. That's a very interesting thing to try to do, but that's the kind of essence of the argument. Okay, so this is it. Ultra soft and minimal zeros goes to Veneziano. Obviously, it's natural to go now to the numerical bootstrap and ask whether we could kind of instantiate some of these assumptions or vice versa. The interplay here seems very disparate from what, for instance, Elvang did, where she assumed supersymmetry and higher point factorization, and we're assuming something very different. Just seeing how these all connect, I think, is an interesting open problem. One thing I want to mention is, while I've talked about the case of Veneziano, this exact logic applies to Virasoro-Shapiro. So you can take a non-planar amplitude, do the same procedure, and bootstrap a Virasoro-Shapiro, again, analytically. Perhaps even more enticingly, this also works at higher point, and really I mean 5 point, which is where we checked. I can tell you the kind of essential workflow is take an amplitude from string theory, and everywhere there was an integer sequence, replace it with an arbitrary sequence. That's kind of morally what you've seen happened here. And crossing asymmetry fixes those types of objects to be the string amplitudes. That's effectively what's happened here. Okay, with that said, I want to talk about just one last feature, which I think is also something which is emerging, which is the interplay of these kinds of ideas with symmetry. Okay, right now I've just talked about unitarity, about gravity, and crossing, but what about a theory that has conserved charges in play? Okay, this is especially interesting in light of things like swampland conditions, higher symmetries. Let's ask about dispersion relations in the presence of charges. Okay. And just as a disclaimer, at no point, at least in this weak coupling story, do we have black holes. Hopefully that was clear. I'm talking about the regime of validity where the heterotic string amplitude is a good approximation. So we're weak coupling below the Planck scale. A lot of the kind of magic that you want to ask about or think about in terms of no global symmetry is distinctly missing from this. And yet you can still say some kind of interesting facts, which I'll tell you. The kind of engine for this was something that Yu-Tin Huang and collaborators wrote, and also Sasha Zhaborev wrote a paper on in terms of thinking about the graviton pole, which is the following. Let's say you give an amplitude that has gravitation in it. Okay, so there's a long-range gravitational force, there's Newton's law. What happens if you write a dispersion relation for Newton's law? Okay, in other words, write down the dispersive representation of the one on T pole that corresponds to graviton exchange. It's just a certain particular Wilson coefficient, like any other one. If you do that, what do you get? You get some expression here. Of course, in general, for an effective field theory, you'd have other corrections, like, say, Gauss-Bonnet terms or what have you. But the leading term, if T is below the cutoff, should be, T is below the cutoff should be this dominant piece. The dispersive argument tells you that, at least for the case of tree-level weakly coupled completions, which is the assumptions of this part of the talk, you can recast this T-channel pole as S and U channel exchanges. Okay? This is just a statement of the dispersion relation. At fixed T, we get the singularities in S and U, and we don't know what's inside these boxes, or inside these sums. There are a bunch of states. They could have any type of identity. What's interesting is that when you have charges, you learn something. Okay? If you imagine scattering, for instance, 2 electrons, E minus, E minus, okay, this would be some process which is a gravitational exchange by the equivalence principle. It has to be non-zero, so the left-hand side cannot be 0, which means the right-hand side is also not 0, which means that one of these terms has to be non-zero. That's interesting because it mandates the presence of new charged particles that are being exchanged. Okay, so this is the connection to kind of completeness. The idea is to take some set of charged seeds. Someone hands you some set of initial particles that are electrically charged, write down a dispersion relation, use Cauchy's theorem, and deduce new charges. So that kind of basic workflow is to assume, as I said, some set of charged states, scatter them through this process, write a dispersion relation for the graviton pole, deduce the states in the S and U channel. So you've now learned that there's new charged particles, and then put it back into your inventory and rescatter them. Just keep doing it over and over. Okay. The key is that once you rescatter them, by the equivalence principle, there's still a graviton pole. There's always a graviton pole for everyone, so you always have this dispersion relation. In case I didn't make it clear, the assumptions of this type of argument are actually much weaker than the ultra-soft or minimal zero. All that stuff was not needed for this. The only assumption is that I have gravity, and the boundary term is gone, and I'm at weak coupling. So the assumption is a weakly coupled UV completion of graviton scattering. Now, what do you get? Okay, so maybe I'll just say in words. What you get is that starting from some fundamental charge seed, every possible tensor product representation you can get from that must appear as some weakly coupled state. One way to think about this is as an explanation for why, post facto explanation for why the heterotic string has a tower of charged states. It's all weakly coupled. I wanted to say one thing, which is that this is kind of secretly both stronger and much weaker than the kind of usual kind of swampland type ideas. This is much weaker than the claim that I could deduce that there is the fundamental charge particle. We're not doing that. We're being handed a particle to scatter. And that's, of course, most of the work of the swampland. But once you have it, what you deduce is a bunch of weakly coupled single particle states that are in tensor products of that fundamental seed, and that's kind of interesting. So yeah, the assumptions again, just to litigate them carefully: tree-level quantum gravity, which is a statement that there's a Born exchange of the graviton. The boundary term vanishes, there's a C charge, and one extra UV condition that I didn't mention, which is just that the UV Reggie behavior is charge blind. We call this the high energy equivalence principle. It just says that the Reggie behavior does not care what your electrical charges are. That turns out to be the most crucial of these, and it implies completeness of the C-generated irreps of G. It's quite powerful and applies to a very broad class of symmetries. Okay, let me stop there with my 1 minute. Hopefully I've been able to convince you that you can learn some new things about classical general relativity using methods from amplitudes. The kind of first bullet here is kind of very much workmanlike. It's about applying something to an experimentally vibrant field which cares about precision. The second is a much different set of questions about how quantum mechanics and general relativity are made consistent. And I think we've learned some things. Okay, it's still not definitive, I would say, personally, but I think it tells us what we would assume to get string theory, and also, importantly, what you'd have to not assume to not have string theory. And with that, let me conclude, and thank you for your attention.
Thanks very much.
Thank you for the beautiful talk. Yep. Somewhere early in the quantum gravity discussion, you assumed that the growth of the amplitudes started to fall off before black hole production.
Mm-hmm.
So I guess we could imagine theories in which that's not the case, right?
Yes.
Where you can't pull them apart.
Yeah.
Is there anything we can say about that?
At present,
situation?
I would say no. I don't have a good no. We thought a little bit about it, and we couldn't find a path towards that. But it's certainly an interesting question. Yeah.
But many of the stuff in the amplitudes, the EFT hedron and so on,
Yeah.
they don't assume that, right?
They don't assume that. We had to distinctly assume more. The null constraint story assumed substantially less. Yeah, so it's not necessarily required. We had to assume it, or we did assume it to get uniqueness. I think we're still at the stage where we don't know kind of which assumptions are fully linearly independent, and that's why I think kind of studying this analytically is a good path forward.
Okay.
But I agree, that's a very interesting question to
Thank you.
understand. Yeah. Thank you.
Hi, great talk. Is the punchline that that the unique ultraviolet completion of Einstein gravity is string theory, or if you sort of modify some of the assumptions you made, about poles,
Right.
etc., whether you can still get the same low energy theory?
Right. My conclusion would just be, given the assumptions we made, the unique conclusion is Veneziano, Virasoro, Shapiro. I can tell you which assumptions I would relax to leave that space. First and foremost, I would frame the kind of weak coupling assumption. It's a big assumption. It's tree-level meromorphic. It's very stringent. You could easily imagine something very strongly coupled, like, let's say, putative asymptotic safety type scenario where it's intrinsically about many multi-graviton exchanges, where it would certainly leave the bootstrap picture that I'm describing. You could also ask about theories that simply don't have nice ultra-soft behavior. That's a perfectly fine, reasonable possibility. You could be less than minimal zeros. You could have more excess objects deviate from the kind of natural minimal object, and that would be fine. And last but not least, you could simply not be Lorentz invariant. Okay, as also hopefully, we understand that that's kind of fraught because of experiments, which actually probe Lorentz invariance, the extreme precision from neutrino propagation. That's constrained, but it's an assumption we've made. So there's many. I'm ready to relax any number of them and think about that space. I think that's very interesting, actually.
Thanks.
It was a very nice talk. Thank you.
Thank you.
I have too many comments to make that, but a few. First of all, I always felt one of the shortcomings of this kind of bootstrap is focusing just on the 4-point amplitude, not the multi-particle amplitude. So constraints of unitarity are very weak. At best, some kind of positivity, elastic scattering. Although, at least at the 5-point level, constraints are beginning to be imposed.
Mm-hmm.
The amplitudes that I wrote, the deformation that I wrote down in '69 had satisfied factorization of the multi-particle amplitudes. So unitarity in perhaps a negative metric, a Hilbert space with negative metric. Of course, that was before even the dual resonance model or string theory was proven to have positive metric. That was non-trivial. And in fact, those generalizations would satisfy unitarity to all orders in a theory which might have negative metric states. Is not even, has an infinite number of deformation parameters, and potentially, I always felt some of them might have real unitarity, positive, definite. Hilbert space, that's not unlikely, since there's no deep symmetry principle as there is in string theory. But they also had something else, which is a rather physical constraint to be applied, I think, which is the growth of the density of states. So in quantum field theory, that, the density of states can only increase like less than e to the m. Whereas in string theory, the degeneracy at the higher levels goes like e to the m.
Right.
And therefore, there's a finite Hagedorn temperature. And the deformations that finite height transition at high temperatures, and the kind of generalizations that factorize to all orders, density of states goes like e to the m to the a, where a is strictly less than 2, but greater than 1. So one obvious physical constraint is that the Hagedorn temperature is positive. That at very low temperatures, the string exists as an object, but at some finite temperature, it perhaps breaks up. That's quite a physical constraint. It would be rather...
That's a great suggestion. That's something we should certainly look into.
Yeah. But it's difficult to look into because that clearly requires discussing the multiplicity of higher states.
It requires you to litigate closely the states that are exchanged.
You really have to know. And the only way you can count the states is to go to arbitrarily high scattering amplitudes. Right, because...
Right.
There's another point which I think, which it would be good to get you guys' opinion on. The asymptotic behavior, Reggie behavior for negative, t, which is a straight line, is very unphysical from the, again, from the point of view of quantum field theory. So this is related to the fixed angle high energy scattering. Okay, that, the way I analyze that with my student with Mendez seems to imply that the amplitude falls off like e to the minus p squared. That's not allowed by any local quantum field theory. The border line is e to the minus p. I actually believe that that's what happens in string theory as well. And it is not due to, it's due to what's called sister trajectories, which come in at fractional values of the slope. Those can be seen in perturbative string theory, but only in multi-particle amplitudes. So they don't occur in the 4-point function. They do occur in the 6-point function. And they occur in all multi-particle amplitudes as well. And they are directly related to the fact that what Mendy and I discovered was that in higher loop corrections to the 4-point function, we kind of conjecture that they wouldn't go like e to the minus p squared, but e to the minus p squared over the genus. So the higher you go in loop corrections, the softer the behavior is. And those are directly related to these sister trajectories which take over. Sister trajectories also have zeros, so anyway, it's a long story.
Right.
But, so again, very good constraint, which again requires higher loop corrections or tying higher loop, if you have higher loop correction as a tree approximation, you close the lines, you get a loop correction to lower point amplitude. So those are kind of correlated, and those constraints, I think, are eventually lead to a fixed angle scattering, which is consistent with locality. And string theory, although it always appears to be in some sense non-local, turns out in the end to be causal, local.
I absolutely agree with all those things. So first of all, we would try to tackle that if we didn't already we're already kind of shackled at tree level. If we could include higher loops, think about this non-perturbatively, that's extremely natural. Regarding the higher point, also an active part of what we're doing is maybe you even know, talking to Grant Remen, thinking about higher point positivity. And I'm totally in agreement that there's a huge number of just positivity constraints that have not been studied. We've been trying to systematize that. We had a recent paper placing new bounds on chiral perturbation theory using 6-point, places an actual non-trivial bound. I think there's a wilderness out there that could be even more constraining. Yeah, so absolutely. Yeah.
Question
hi.
there.
Yeah, thanks for a wonderful talk. So I'm wondering about the dimension of space-time, which you seem to be assuming. But I wonder if you can repeat this analysis starting in 4 dimensions and asking, for example, about n equals 8 supergravity, or about n equals 4 super Young.
Yes.
I mean, of course, n equals 4 super Young Mills has, well, there's questions because of conformal invariance and so on.
Right.
But for n equals 8 supergravity, there would be a question whether you can basically discover the theory in this way.
Yes. I would say for the null constraints and for the primal bootstrap, that's extremely natural because the unitarity constraint itself depends on a partial wave decomposition that's highly d-dimensional. So in principle, you could do the same exercise with various dimensions and ask questions about compactifications, about other, if you like, other types of theories. So indeed, that's just another dial that we often float that I didn't even mention. But
So in 4 dimensions, has this been done?
Sorry, you mean floating upwards from, sorry.
No, 4 dimensions, and let's say, you know, thinking about n equals 8 supergravity. Do you know if this has been done?
I don't know offhand, possibly. Yeah, that I don't know, actually. It's quite likely it's in one of these papers I actually referenced, but I don't know, actually. I could look up and tell you, yeah.
Thank you.
Okay, well, we'll take maybe one last question very quickly.
I'll be brief. Can you, here,
yeah.
Can you obtain amplitudes that are not Veneziano in that workflow you presented?
No, not given the assumptions we made, no.
But are you able to modify these assumptions and target other string amplitudes?
In principle, yeah. You have to just relax with the assumptions, the ones I stated. Yeah.
Okay, thank you.
Okay, so let's thank Clifford again for a very stimulating talk. Before you go, there's an announcement from the organizer.
Yeah, very brief announcement. Dear participants, please enjoy the free public lecture by Professor David Gross, String Theory, Successes, Surprises, and Challenges. The lecture will be here in this room. The lecture will start at 7 p.m. There is no need for additional registration. Just bring your conference badge with you. Thank you.